Hello, my name is Mary Lou, and this is my Lab 1 for charged tapes. The purpose is to prepare charged pieces of clear tape, observe their interactions with tape and other objects, and estimate the charge on one piece of the tape. Then we make a model to simulate the interactions between two pieces of charged tape. A brief overview of results show that we find the charged tape has a positive charge of 2.3 times 10 to the negative 8 coulombs and has lost 1.5 times 10 to the 11th electrons. For the fundamental principles, we first have Coulomb's law, which states that the force of electricity equals Coulomb's constant K, which is shown below. Q, which is charges of each particle multiplied by each other, divided by R, which is the distance between the centers of the two charges, times R hat. We also have Newton's third law, which states for every action there is an equal and opposite reaction, which is why we have FAB equals negative FAB. Considering this, our key assumptions for the lab is that we ignore any kind of air resistance. Both tapes have the same charge, and that at the center of the tape it acts as a point charge. For the procedure, we were to charge the U-tapes by quickly peeling them off a base tape, observe the interactions between two U-tapes, and then between a U-tape and a charged plastic object. Then we suspend one U-tape from a surface between two objects so it hangs freely. Then we bring the second U-tape beneath it and observe how their interactions change with separation distance. In this experiment, our system was the U-shape that was suspended in the air, and the surroundings was the U-tape that was being held to it, as well as everything else around. It was found that two U-tapes will repel, U-tape and a hand will attract, a U-tape and a charged pen will also attract. We know the pen is negatively charged because rubbing the pen through hair transfers electrons from the hair to the pen, giving the pen a net negative charge. The observed attraction between negatively charged pen and the U-tape suggests that the tape has a net positive charge. This is the data we collected, including tape length and width, which helps us calculate the area. We also found our mass and our separation value R, which was 0.05 meters. We obviously know Coulomb's constant. We can also calculate the number of atoms, which is dividing surface area by atom area, which we found to be 3.8 times 10 to the 17th. We can calculate the electric force on the suspended U-tape by finding our gravitational force, which is multiplying our mass to gravity, or gravitational constant of negative 9.81. This would be negative 1.96 times 10 to the negative third newtons, and electric force would be the negation of gravitational force because the tape is at equilibrium. This is the code for the simulation. In the first picture on the left, we can see all of the constants I used, which we just talked about in the previous slide, such as Coulomb's constant, gravitational acceleration, length, width, mass, and separation distance. In the calculation portion, we can see how the equations for calculating the gravitational and electric forces on the suspended U-tape. Down below is the equation for calculating charge using Coulomb's law, the equation for calculating missing electrons, and the equation for calculating total atoms, which was previously found. Here is what the code produced for my simulation. As seen on the image, the red ball is the top suspended U-tape and the blue ball is the held U-tape. The green arrow represents the force of gravity and the orange arrow represents the force of electricity, which are the same length. Below are all the calculations that my code outputs. When the tape is ripped from the base, it becomes positively charged by losing electrons. When suspended, the tape floats at a constant height, meaning the net force on it is 0. At this point, the upward electric force balances the downward gravitational force, allowing us to estimate the tape's charge and calculate the number of electrons lost. Some possible sources of error are tape handling, as touching the sticky part of the tape or rubbing it unevenly can alter the amount of charge. Measuring inaccuracies, as in errors in measuring separation distance or tape mass, can affect calculations. Calculation errors may be simple, rounding errors, or measurement inaccuracies, such as errors in measuring separation distance or tape mass, can affect calculations of force and charge. What if and why questions? What if electrons were positive and protons negative? The sign of all charges would be reversed. Observations would look the same in behavior, but their direction of attraction and repulsion would switch. For example, tapes that previously repelled each other would now attract, and tapes that were attracted to neutral objects would repel. Why handle the charged tapes as little as possible? Touching the tapes allows electrons to move, which changes the tape's charge. Contact with hands or other objects can discharge the tape, reducing the observed electrostatic interactions and make the experiment less accurate. Thank you.